So, hey, Mr. Barton. So, I will start from the very beginning. So, this is a slide that we made for Friday's presentation. So, with this slide, I'll be able to to explain all these things that you've listed right here. So, I'm gonna start um, by telling you some of our assumptions. So our assumptions first is that there is nothing but water in the lake. So there's not going to be any people swimming in the lake when the lake is full, and there's not going to be any events hold in the lake, or there's not going to be any boats, any ships, anything. Just there's just water and salt. And our second assumption is that wind speed will not affect the evaporation rate of the water body. Yeah, this is pretty obvious right there. And the salinity of the water remains constant, meaning that the salinity will not change dramatically like during a certain period, which is triggered by any sort of chemicals down the river. No, it's not going to happen. So the salinity is always going to remain at a certain amount. And the shape is like a spinning top. So a spinning top, something like this, a spinning top. So our shape is something like this, a spinning top. This is our shape because we assume that the from the shallowest point of the lake till till somewhere around here, the lake, the depth of the lake will not be changing so fast. Like the radius that we calculated later on is 54.5 kilometer. So like it's almost like in between 54.9 kilometer to about like here's like 10 or 9 kilometers from the origin. The depth will not change that much, but however, like when it gets more and more inside the circle, more and more close to the origin right here, the depth is gonna change like suddenly, just from let's say from 4 meters to 5 meters, then from 5 to 6 meters. Yeah, so we assume that this shape is pretty safe. And our fifth assumption is that there should be no natural disaster or geographical events occurred during this testing period. Yes. So the Earth is not moving, and there's not going to be anything affects our experiment. Yeah. So, and the math that we used to calculate the volume is actually derived from a method in calculus called disk method. So this method is used to calculate this type of shape with cross section that we assume the cross section is going to be circles or the cylinders. Yeah, and okay, so we kind of gathered the data from the website, and the websites are right there. Where is it? Probably it's right there. Okay, it's right there. No, So some of those websites we've got the citation down, but we didn't like we haven't put it up there yet, but it's there. Yeah. So we gathered our data from some websites, and we got a point that that we've got enough information to do this calculation. So for this circle right here, we assume that this was going to be a circle, and we've already known the surface area of the circle, so it's actually pretty straightforward for us to calculate the radius of this circle, which turned out to be 54.9 kilometer, and and the depths are known already, is 0.006 kilometer. So right now at this point, uh, we've gotten the maximum point of this function right here, y equals ax squared. Yeah, so we wanted to know the value of a, and in order to do so, we just simply plug in the maximum point here, 0.006 and 54.9. Then we got the a equals to 1527610. Yeah, and because our cross section is a cylinder, and the volume of the cylinder is height times times circles, the area of the circle. So the areas of the circle times height. Then we finally got to this stage here, and we plug it into this integral thing, and we finally got our volume to be 11.4. Yeah, roughly 11.4. And so later on, we found that the evaporation rate for this lake is 2.3 meters per year, and we take this into account. Then we do a bit of computation here. So we first went off from point 0.006, then we cut down 2.3 meters, then the integral turned out to be 0.0037. Then we calculate the first time, and the first time it actually took away 10 cubic kilometer already. And the second time we calculated from with the same amount of water loss. No, not water loss. The reduction in the height, and it turned out to take away our volume of 1 cubic kilometer. Then the rest, we have 1.4 meter left, so we just simply plug it in into this kind of very simple function right here. So it's 1.4 meters over 2.3 meters, doing like the percentage of this 1.4 meter and this 2.3 meter. Then we got the percentage that we times 12 months a year. Then we got it these 7 months or so. Then we use the remainder, the 0.3. Then we times the 30 days a month, so we got this exact number, 9 days. 9 days after 7 months, and this 2 years of drying period, and it will be completely dry. And so initially we were gonna take the soil loss and the salinity and the precipitation into account. However, later we found out that the precipitation did too little. Like they barely did anything to the volume as whole. So and so is the case with the salinity. The salinity of the water was not even 0.002%. So we decided that we won't take into account. Like I know a lot of people they were saying that the salinities in this lake is like really high, but since we are assuming that this lake was full at the beginning of this experiment, since it's full and the amount of salt that's remained, the salt crust that's remained in the bottom of the lake will not matter that much. Like maybe at the end, like as the volume decreases down, and as this experiment, like this time period gets to the end, the the salinity might play a more and more important role in this calculation. However, at the beginning, uh, at the beginning, we didn't we didn't take into account since the salinity was too little, like too small for us to like to regard it as something that matters. So so yeah, I think that's basically it, and I think I've answered all of these questions. And yeah, thank you for your listening, and I guess it's approximately 9 minutes of speaking. Yeah. So, okay.